Thank you for the introduction. Thank you, Giuseppe, for the invitation, and the University of Pisa for organizing this interesting web seminar. As said, I am Federico Uriati, PhD student at the University of Parma. And today I would like to present you an overview on the research topic that we are developing in our group, in particular in relation with the optimization, production, and testing of components produced with additive manufacturing, and in particular in relation with the evaluation of experimental fatigue strength. This presentation, I will briefly introduce the topic that, of course, we already widely discussed, the research framework in which we are involved into, the presentation of the proposal of additive manufacturing integrated design workflow with the step that we recognized and selected that need to be followed for the definition and the modeling of a additive manufacturing problem. And after that, the presentation of a case study that we developed based on the previous workflow. In the end, will be reported some conclusion and future outlook. As said, additive manufacturing is an innovative manufacturing technology that, in particular, in relation with laser powder bed fusion, allows starting from metallic powder, the realization of components characterized by complex geometry and characterized by internal features that are very difficult or almost impossible to be produced with the traditional subtractive methods. For this reason, recognize the advantages of the technology. Our objective is to investigate the software tool and methods that designer and technologists needs to know, at least for enhancing the potential of the additive manufacturing technology. And here we developed and want to propose an integrated workflow with the definition of the tools for the design, the step to follow for the pre-production, production of the component, and the method for setting up a test to evaluate the mechanical properties of additive manufacturing component. The research framework in which we are involved to is important to underline that luckily we have a strict collaboration with our industrial partner BMIT, that is one of the probably biggest additive manufacturing industry in Europe that has many additive manufacturing system, and their internal research guarantees us to have the best quality on the process parameter selection, the material selection itself, and also they have to guarantee their customer the best result, the optimization of the process for the minimization of defects and problem in general. For this reason, we will have access to the realization of high quality component, and for this work, we will have the opportunity to produce our part with the technology that is direct metal laser sintering, and the material on which we focused was aluminum silicon magnesium alloy. As said, the proposal is the identification of the step to build an integrated design workflow from the design to the production and testing of additive manufacturing components. The first step is the part selection, of course, that needs to be interesting and would have sense to produce with additive manufacturing. And also some parts that would be producible with additive manufacturing but requires optimization or have complex geometry not obtainable with traditional technology. After the part selection, important to define the part itself in the sense of defining the dimensional constraint, defining the materials of interest, and the technical specification we want to achieve. and also the features, the part itself, if present some part that could be generate problem in the modeling part. After the part selection and definition, it's possible to introduce the optimization of the part, in particular in relation with topology optimization, and that requires the definition of the objectives of the optimization, the definition of the boundary condition and the loads that are applied to the part. And after the numerical optimization gives the result, the optimal result, is important to perform a redesign of the component, because as we will see, the result that is the output of the optimization is not directly producible. And after the modeling of the final design of the final geometry, perform the final validation, the final element validation. Usually, the link between the numerical environment and the simulation environment is difficult to achieve. Now it's okay. So, since, as I said, the collaboration with the industrial partner allows to jump into the production field, allow to have a direct contact with all the steps that are included in the production. So we perform an additive manufacturing process simulation. We made a speed the preparation of the job, and also all the post-processing treatment that needs to be performed also in relation with the detrimental effect that you already explained widely before. The last step that we had set up and we are performing right in this period is the laboratory testing and evaluation of the mechanical properties of the real component in the real produced component. The case study that we selected is the suspension arm of a sports car, and in particular we selected the lower arm. And defining the design space, we needed to, since this is a case study and let's say, yes, a study that was of interest for our research, we scaled the part and defined the constraint with the objective to simplify the load condition and the constraint condition, and also to replicate easily all the boundary condition on the testing machine. So you can see here the design of the final part that we selected. And then we perform the topology optimization of the part using a specific software, Inspire, that allows to introduce the optimization objective that for us were the minimization of the mass and the maximization of the stiffness. With the software is possible to introduce different constraints, in particular relation with the manufacturing that we want to use for the production of the part, and of course in our case is related with additive manufacturing and overhanging of the part of the surfaces, and also different symmetry as trial were introduced. Here it's impossible to observe different results that difference from each other because of the boundary condition introduced, but in particular we selected the last one that was the best solution because it reached the best stiffness to weight ratio. So we were satisfied by this solution and we proceeded to select this part. As I mentioned before, the output of the simulation, of the optimization, is not directly producible because it presents irregularities and surface that could be problematic for the loading, so for the real application and the real production. So it's necessary to apply and to develop a remodeling of the part, and usually, or at least it's easier to use an organic modeler that for us was Altair Inspire, also from the same software house, that allows to model organic shape and smooth surface that are better producible with the technology. After the remodeling and the definition of the final shape and the final geometry that we want to expect, we performed the final file element validation, where we were able to observe where the areas most stressed and where will probably occur the crack initiation or the failure in total. The step and the link between the modeling and the 3D model and the production is usually not so easy to achieve for a research group, but luckily, as I said, with the help of our partner, we had access to the technology and the production directly. So we were able to produce our part using a SLM system and product the part with the aluminum alloy. And here are reported some of the process parameters used for the preparation of the part, and also the heat treatment that that the part underwent after the production. The preprocessing, the first step of the production part, is the preprocessing, as I said, so the preparation of the build job, where it is necessary to define and select the best orientation of the part. And in this case, the software Materialize Magic is used for the definition and the observation where the support needs to be located, and also the additive manufacturing simulation process needs to be performed to observe the evaluation, to observe the deformation, if the deformation are too high and could generate fail during the process or the big damage on the part, or if some residual stress or too high residual stress would be generated and would be create problem on the part. So we performed these two steps, and we selected two different orientation because we wanted to have two different orientation with the aim to see if the different orientation generate different behavior in the fatigue, in the mechanical properties during the testing. And so after the selection of the two best orientation, we generate the supports. And also I wanted to underline that on the same build job were produced also 4 sets of miniature specimen that we will use to perform dedicated fatigue characterization, and also Amphion calibration specimen. Amphion, so I didn't mention, I only reported the images. Amphion is the software that we used for the process simulation. So we produced the Amphion calibration specimen to implement the process simulation and to observe how the stress distribution, residual stress distribution, intervene into the process. Those are some pictures of the build job after the production. It's possible to see the Amphion calibration specimen, the first set of miniature specimen that we will use for the characterization of the fatigue strength using the fatigue testing methodology based on the loading of the miniature specimen with alternated loading, alternated bending, that maybe someone of you may know. And also here reporting the name, the indication of the 2 different orientation, A and B. The post-processing after the production include the heat treatment, the support removal, and the surface finishing that need to be performed usually if as some of your previous work, we are not interested in evaluate directly the as-built surface state, but also to avoid all the problem that could be related to the morphology of the as-built, the surfaces of additive manufactured component. So in this case, the choice was to sandblast the surfaces and to remove the irregularities and the detrimental features that are introduced by the presence of the support. Then the last step that is running now, and we started the first step on Tuesday. Actually, we designed the setup, experimental setup, and using the finite element analysis, we tried to forecast the location of the crack initiation and the location where the crack will occur. We define during the experimental setup as well the definition of the loss step that we want to perform to characterize the fatigue limit of the real part and to forecast the real life of the real component produced with this technology. In conclusion, we were able to develop and to identify the step for the integrated workflow with the step that we need to be performed during the design and development of additive manufacturing component and the testing of a real component. The high quality of the material and of the technology is guaranteed from the industrial department, and also the recognition of the different software and the many software that need to be used during the design process and the workflow itself are defined, and we were able to identify all the software that needs to be known from the designer, from the technologies. As I said, the experimental fatigue strength evaluation is in progress, the real component in these days, and the future work, the future test on the specimen will be oriented on the provision of the performance and also in relation with the orientation and the effect that orientation itself and the surface morphology has on the fatigue performance, and how the orientation and the presence of particular condition of the surface or the support position have introduced on the mechanical and the fatigue properties. Thank you for the attention, and thank you for the opportunity. And if you have questions, you can ask me or send me some email. Thank you.